Okay, so I wanted to run through a few slides related to the things that we talked about earlier today with respect to plate tectonics and the different kinds of rocks. So let's see if I can get this to work. So first, some plate tectonic stuff. So here's a picture of the Earth showing the major tectonic plate boundaries outlined in different colors. I'm going to use my mouse here and see if this works. So this line that I'm tracing down the middle of the Atlantic Ocean, which is the boundary between the South American plate and the African plate, further north, the North American plate and Eurasian plate, that's the Mid-Atlantic Ridge, and that is the place where oceanic crust is spreading. It's spreading to the east here, pushing Eurasia to the right, to the east, and it's spreading on the left-hand side or the west side of the ridge. It's spreading this way, pushing North America to the west. So North America and South America are moving west, and Africa and Eurasia are moving east because of spreading new oceanic crust coming from this line. Here we've got the Pacific Ocean, and part of the Pacific Ocean is underlain by this bit of oceanic crust called the Nazca Plate that is moving east. As South America moves west, they collide. South America's continental crust, the Nazca Plate is oceanic crust, and so you get subduction there where the Nazca Plate dives underneath South America. Up here, you can see a little bit of the Pacific Plate and the North American Plate in sort of sliding past each other. It's a little hard to tell from this angle, but that's the San Andreas Fault. And so forth. Over here, we can see the Indian Plate, which used to be its own tectonic plate, has collided with the Eurasian Plate. And this boundary right here basically traces the path of the Himalayas, where India is mashing its way north into Eurasia. This is a more realistic view of what the world looks like if you were to strip all of the water off. And again, you see here the Mid-Atlantic Ridge running right down here. This is where new oceanic crust is created, pushing North America this way and Eurasia this way, South America this way, and Africa this way. Subduction of the Nazca Plate here, below South America, and so forth. You can see all the different mountain ranges too that were formed in ancient history by the collision of continents, the Appalachians here, which interestingly hop over and extend up here. The Caledonides and the Appalachians were at one time part of the same mountain range. And the way you can see that is if you imagine reversing time so that Africa and Europe move back towards the Mid-Atlantic Ridge and North America and South America move back towards the Mid-Atlantic Ridge. When they all join up here into a giant, it's called a supercontinent, this mountain range and this mountain range would be one and the same. All right, we talked about the Wilson cycle. The Wilson cycle is the life cycle of oceans. You can see down here, this is the very northern part of the East African Rift, which is the beginning of an ocean basin. Here and here, the Red Sea and the Gulf of Aden, those are the young oceans that formed a few million years ago. They had something that looked a lot like this, a rift. This is a view down a rift valley. So as the crust stretches, the crust thins and the center drops down here, and the sides are left hoisted up a little bit onto the side. As those valleys, as those long linear seas continue to widen, we get something like the Atlantic, which is something we've already looked at. Here you can see the Mediterranean, which is this old ancient linear sea that's about to be squeezed shut as Africa and Europe begin very, very slowly, or continue very, very slowly to move towards each other. South America here, these mountains that run all the way down the sides of the west coast of South America are the Andes, and they are volcanic. And those volcanoes are formed in association with the subduction of this oceanic crust here. As it moves to the east, it dives down underneath the continent of South America, causes magma to form, which rises up or melt and produce these volcanoes. There's a cross-section of a subduction zone. So this is South America. These would be the Andes, essentially. This would be the South American continent. This is the oceanic crust coming in from the Pacific that's diving down here Each one of these X's is supposed to be and O's, those are supposed to be earthquakes. Here is the magma forming in the subduction zone that then rises up nice and hot and buoyant to erupt out of the surface as volcanoes and so forth. All right, we talked about the different kinds of rocks. Sedimentary rocks, these are, this is looking under a microscope at tiny little grains of sand. You can see the sand, some of the sand is clear and glassy. Those would be quartz grains. Some of them are multicolored. This might be a little bit of some sort of rock like a lava or something like that. Those are the loose grains. This is a photograph of a slice of rock made from grains like that. They've been cemented together by natural glues. And the blue here is this is looking under a microscope. The blue here is actually the pore space. It's the empty space between the grains. The reason I'm showing you this is that even things like sedimentary rocks, which are compacted bits of other material, they have empty spaces in them, and that's really important for our class because that's where the water goes, and that's where the water will be stored and be transferred through the ground. In terms of sedimentary rocks, they're deposited in lots of different environments, but the vast majority of them are deposited below sea level. There are a couple of exceptions, and you can see some here. We'll look at them. But basically, the rocks that are exposed above sea level get washed down by rivers and deposited in the shallow coastal margins here. Some of them get washed further out to sea, but the vast majority are deposited on the sides of continents. This is a couple of different curves that have been reconstructed by geologists for sea level. This is on the y-axis over here. This is the height of sea level relative to today. So 0 is the current sea level. This is in meters. So if you want to convert it to feet, multiply by about 3. So if you're at this level right here at 100, that would tell you that sea level is 300 feet higher than today. This would be at 200, would be 600 feet and so forth. And you can see if you go way back to about 450 million years ago, the time when a lot of Iowa was being flooded by and was under these shallow seas, it's a little bit of a discrepancy here, but sea level was about, what, 6, 7, 800 feet deeper than it is today. So that's just enough to flood big parts of Iowa and lots of the Midwest and produce the limestones and so forth that we see here. And when sea level was higher, this is what chunks of North America would look like. You can see Florida outlined here. This was a time period called the Cretaceous, which is the last time period in the Mesozoic when the dinosaurs were walking around. So basically, if you were in Iowa and you got in your car at this time, you drove to western Iowa, you'd hit this beach and you would see this big interior seaway. And in these shallow waters over big chunks of North America, that's where all these things like limestones were being deposited in great abundance. This is a photograph from the bottom of the shallow bay in the Bahamas, and all of that white muddy stuff you see down there on the floor, on the sea floor, that's eventually going to become limestone. That's the broken up bits of coral and different shells. And also, actually, there's a little bit of material, calcium carbonate material, that forms on these sides of these grasses and then falls and flakes off. But these huge carbonate mud factories, as they're called, just pull calcium carbonate and oxygen out of the ocean, turn it into a mineral, and then drop it on the sea floor, where eventually it will be turned into limestone. This is what limestone looks like today. You can see the horizontal layers and the sort of light tan color, which is pretty common. You also have shales, which are much finer grained, made of muds. They're typically pretty soft. You can see how this hillside is kind of eroding away because the shales are so soft. I'm skipping through some of these slides. Out in the deep oceans, you have most of the ocean floor being made not up of sand or clay because it's too far out into the ocean to wash that stuff from the continents. So instead, what you have are the shells of these little organisms that are floating around in the water column. They make their shells also mostly out of calcium carbonate, although some make them out of quartz as well, which is silicon dioxide, like glass. And when they settle to the bottom of the ocean, they do so very, very slowly. So the rate at which sediment piles up in the deep oceans is very, very slow. Sedimentary rocks sometimes give us clues, direct clues to where they were formed. This is a, a little inlet in some estuary someplace, some tidal flat, and you can see the little ripple marks running across. And there is a rock made from similar kinds of deposits that's now been solidified, it's been cemented and turned vertically. But you can see those same ripple marks. So this is the modern, and this is millions and millions of years old, but basically the same thing. We have ancient desert or modern deserts with blowing sand forming these big dunes. And sometimes those dunes get cemented and solidified and turned into rock. And we see things that look like this. There's a person for scale, but these big upward angling lines that are then cut off by these horizontal lines. This is the sedimentary structure that's characteristic of ancient dune fields. Sand dunes make excellent, excellent places to store and transmit water. And so seeing something like this would make you very excited if you were a hydrogeologist, but that's more for later. There's a crummy picture of a sandstone. In some cases, on the flanks of mountains, you have tons and tons of gravel and sand that are washed off the sides and deposited. You can see this is, I believe, in Death Valley. You can see the road actually driving along the edge of this thing. It's pretty stable. If it was active, the road would be constantly being washed out. These are called alluvial fans, and they represent lots of coarse grained material that they're small, but they make excellent places to store water as well. An alluvial fan would have sediment that when solidified and turned into rock might look something like this. Lots of big stuff and little stuff all jumbled together. It's called a conglomerate. And there's another big picture of these coalescing alluvial fans. And then finally, we have these river deposits here. You can see the sands and the gravels and that sort of thing, which can be left behind. Okay, igneous rocks. These are rocks that form from a melt. These are sort of a lava. They can form volcanoes, small volcanoes, big volcanoes like this one in the Pacific Northwest. And lava can form, as I've just shown you, volcanoes. It can form these lavas that flow across the land surface, but lots and lots of volcanic rock, in fact, probably most of volcanic rock, is preserved inside the ground. It doesn't make its way all the way up to the surface. It cools and solidifies inside the crust. And then through erosion of the overlying rocks and uplift of the crust, it can be exposed at the surface. This is Half Dome and El Capitan in Yosemite National Park. And all of the rocks that you see here are granite, like you might have in a granite countertop, but these were formed miles down inside the earth by melt that stopped moving upward, formed these big pockets, and slowly cooled and crystallized into rock. The size of those granites in the Sierra in California are actually this big. This is called the Sierra Nevada Mountains. This is the Sierra Nevada batholith. The batholith is basically just an accumulation of giant blobs of magma, of melt, that's solidified to a solid inside the Earth's crust. And then finally, we have metamorphic rocks. We're not going to spend much time on these at all, but suffice it to say that these generally are consequential, meaning that they're really spatially relevant. They span lots of distance when they form in ancient mountain belts. And here in the northern Appalachians of southern Vermont, we have a whole series of metamorphic rocks lined north to south. You can see the scale here. This is 25 miles. And each one of these different zones reflects a different temperature and pressure that the rocks there were squeezed and heated to. So this is the kind of thing that you'd expect to find metamorphism over very, very large areas. Part of that metamorphism forms all kinds of different rocks like these. These are slates, which are what make up the chalkboards in Norton geology. And here are some of the rocks. Slates up in the top and gneisses down in the bottom, schists in the middle, so forth. Here's a quick geologic map of North America. And basically what I wanted to point out here is over here on the east, you see the lines are kind of linear, the arrangement of the different colors. Each color is basically, think of it as a different age of rock. And so the fact that these rocks are all linear over in here tells you that they've been squeezed. It's like compressing an accordion. Over here, they're linear, but they're separate. They kind of alternate, red and brown and red and brown. Over here, in fact, it's the opposite. It's like they've been pulled apart. Here we have the Rocky Mountains. You can see they've been kind of squeezed. But here in the middle, there are big stretches of area where it's all just one color. See, this is all blue, and this is all green, and this is all pink. When you see areas like that, what that's telling you is that the rocks are flat. So the same layer of rock is extending across the land surface for a long distance. So here in the middle of the United States, we have flat deposited rocks that have never been tilted because we're a long way from a plate boundary. Over here in the Western United States and over here in the Eastern United States, there have been tectonic activities in the past. And as a result, the rocks are all jumbled up. Okay. Let's see if I can stop this thing.